Hello, folks. So we're back after a bit of a break, and what I wanted to do today was I have a repo here, this dynamic Datalog repo, and it has an issue filed against it. And I think it's an interesting repo, and the issue is sort of interesting, and I think I know what it's about and how to fix it. So I thought we would do that. There's some setup that's required, of course. Dynamic Datalog is a repo that has 3 Datalog problems, and they're meant to be sort of interesting, I suppose. They're not just simple Datalog problems. It's not just transitive closure or something like that. There are these 3 problems here. One of them is the CRDT problem, and I'll talk you through what it is, what the algorithm is, how it works, that sort of thing. But this is the one that has, well, I'm sure many of them have problems, but this is the one that has the issue filed against it. So that issue, if we swing over that, is, there aren't a lot of issues here. It's not a very popular repository, but this is a good question, which is essentially that if you try to run the CRDT thing, it runs, it's not so bad. It takes 2 seconds or so, something like that. But if you try to use more workers, it doesn't get any faster. And probably we find out it eventually gets slower, actually. It looks like it immediately gets slower. And that's perhaps surprising. It's it happens a bunch, but it's reasonable for someone to say, what's going on here? Why is this going slower with more workers? And I think I know the answer, and we're going to sort of walk through what that is and how to fix it and stuff like that. But we should probably start with what is the actual problem. So the repo, unfortunately, isn't a great place to learn what is the actual problem. There is a Datalog program that we can follow along there, but I'm just going to start instead by drawing some pictures about what's going on here. This is what I understand to be the RGA CRDT data structure. And this is commonly used for editing, for collaborative editing. And the intent is, like, you want to give the appearance of a large unbounded buffer that people might have multiple cursors into, and they're typing, and you want their typing to be reconciled pleasantly. So if 2 people are typing and pointed sort of at roughly the same part of the text, you don't really want them to override each other's work or stuff like that. And this is an algorithm that tries to make that easy. Actually, sorry, I should step back just a little bit and say, what CRDT, potentially you're not aware of what that is. So CRDT is, I don't even remember the acronym, to be honest. It's something like conflict resistant or resilient or whatever, resistant data type or something. I don't know. But the intent is it's a data structure definition, so it's some data and some ways that you can interact with it, which has the property that if multiple people try to use it at the same time without synchronization, so you might, like a text buffer that multiple people are trying to edit at the same time, maybe this is like a Google Doc, something like that. A CRDT has some sort of pleasant property about the ultimate use, concurrent use of the data type by multiple people. And they're meant to be sort of nice, as a good way to avoid synchronization in settings where synchronization is either expensive or just unlikely, right? If you're editing on your laptop and you're on a train and you go into a tunnel, and there's just, you're not going to be able to synchronize your buffers in anything other than 5 minutes when you come out the other side of the tunnel. So the goal is for them to try to put together these data types that are conflict resistant in a way that we'll see an example in just a moment that maybe will make this a bit more clear. Actually, we'll leap right to this RGA thing. I have no idea what RGA stands for. The intent is that it tries to model like a nice big text document, right? That multiple people are potentially writing into, maybe at the same time, maybe in different places, maybe in the same place, or maybe you write something here and then someone else leaps in and tries to, delete a word or put another sentence in between 2 sentences you've written. Weird, crazy things like this that you're supposed to support. But you can understand potentially how if you just gave people the same buffer, just like a big allocated pile of text, it'd be a disaster. People would start overwriting everything. So the model that RGA takes for this is to say, well, let's not treat text as a big buffer anywhere. Let's treat it, in a sense, let's treat it as a linked list of, it could be super primitive, linked list of characters, right? So, and it's going to end up being more than a linked list. So if you know how RGA works, just bear with me. So the rough gist is that we're going to, if you want to type hello, you might put in the letter H, and then follow that with the letter E pointing to hello. Follow that with, this is going to get old really quick. Follow that with an L. And so on and so on and so on, where each new bit of information that you drop in, each new letter sort of points at where it's supposed to follow. And in principle, this is great. Like if you just keep doing this, you'll end up with a nice linked list describing all of your text. Linked list isn't a brilliant way necessarily to do a text buffer, but it's going to have a good property in just a moment. Now, what happens here if you and someone else conflict? So your cursor is always at the end of what you're typing. That's totally fine. So the algorithm is roughly like, look where your cursor is, grab the name of the thing just before your cursor, and then splat down a new symbol right afterwards and point backwards. Now, if someone else wanted to sort of drop in there and maybe they wanted to land right between H, E, and LL and start typing some new stuff, well, in principle, they could do that. In fact, the system doesn't necessarily know that they're not you. So let's imagine that someone saw HE and then didn't know how you're going to finish it, and maybe like you went offline right at this moment. So they thought, brilliant, I'll just write some stuff here. In fact, maybe I'll put a space and then I'll write some more stuff like he said or something like that. It puts an S and I don't know, A. So this is now a little bit of a fork, essentially. Someone has shown up and said, well, I also believe that I'm editing at this spot between E and L here. Let me go and do that. And what RGA essentially does is say, this is fine. We're going to have to find a way to put this back together afterwards. We're going to turn it into one contiguous line of text, essentially, or one contiguous buffer, using some rules that are relatively stable in the sense that they're not going to be order dependent. We're not going to have to figure out whether the L here or the space came first or anything like that. These concepts generally don't work out very well in CRDTs. And the whole buffer eventually is there's some root, basically the very beginning of the document, off of which everything else dangles. And the job basically of whoever needs to go and implement RGA is to pick up all of the pieces. If people have just slotted in random new edits, teeing off of various moments in other people's or even their own other people's lines of text. So as I understand it, RGA is a way to do this. And I don't know how much RGA specifically prescribes, but there's a not insane way to go out and do this, which is to say everyone just keeps adding in new things. Nothing gets deleted, or at least not in the... No information is destroyed here, so you can only put down new symbols, point at other symbols. And what we're going to have to do for every moment that there's a little bit of ambiguity, for example, this E here has two nodes that might follow, but we call them two children. This is going to be sort of tree structured if we rotate things like so. It's got two children. We need to figure out which of them comes first. And there's going to be a rule. Essentially, when you splat down each new node here, you point not only at some... Well, you provide an identifier, like the child's identifier, and you also name the parent to which you connect. Child identifier, this needs to be something like a GUID, a global unique identifier. And one way to do that, for example, is it could be your username and a sequence number or something. It can be arbitrary. It doesn't have to be random or anything complicated like that. But it's a thing that will be unambiguous when we compare these two things. Everyone will see the same thing, and we can break ties of who among E's children should be next. Sorry, it's not a linkage there. It's a pure relationship. We can break ties by using these GUIDs. Essentially, look at maybe these two operators, these two nodes, the space and the L, and say, well, who has the lesser GUID? Let's put them first. And it's arbitrary. And the goal isn't necessarily to find a semantically sane way to reconcile this. I'd be inclined to say, for example, that the space should get priority here because if the contributor of the E and the L are the same, that person probably just kept typing, and the person with the space showed up and probably intentionally tried to drop something in between the two of them. But I think those sorts of questions, how to do this tie breaking to give the best ergonomic experiences outside the scope of what we're going to talk about here. And instead, we're just going to have a rule that tells us which of these two things break ties, and then the order on the whole sequence, I guess, like the buffer of text, is going to be a pre-order traversal of the tree. So essentially we're going to go H, then E, then I guess we're breaking with space going first. Space S, question mark A L L, and this is one take on how to do things, but it's relatively the same. If someone else shows up and does something really surprising, like maybe drops in another really low GUIDed node in there that tries to say hi instead of hello, they can. So it can be disruptive. That's totally fine. Like, you should be allowed to go back to the beginning of the text and do some editing there, of course. But yeah, that's roughly the gist. And if you imagine two people working on this, there's sort of two threads of work that might continue independently. They don't conflict all over the place, and there's just some reconciliation that happens after the fact. And fortunately, like the main good property it has is that it happens unambiguously. You and I will both see the same reconciliation if we're both editing on things, and eventually see all the same sets of updates. So that's roughly the algorithm. Why are we talking about it, though? So the story over here with this CRDT issue, but also with the CRDT project that's in this dynamic Datalog thing, is some folks, Martin Kleppmann specifically, reached out to me with some collaborators at University of Cambridge with the idea that maybe you could use a Datalog engine, you could use Datalog as a specification language for how this RGA algorithm is meant to behave, and then use the fact that there are incremental Datalog engines out there, ones that can absorb new facts and keep running, as the implementation. Right? So the meta algorithm then for RGA or other CRDTs might be, step one, write a Datalog program down, a bunch of derivation rules. Step two, have everyone just start contributing facts, input facts. And these input facts here are these child to parent links, as well as some content attached to them. As these new facts are contributed, often you would have a complicated, like, well, geez, how do we increment, blah, blah, blah. And their idea was, why not just let Datalog figure that out? Like, let someone else who's good at building compute engines, ideally incrementally updated compute engines, be in charge of putting together, keeping the solution up to date to sort of show you in your text editor or what have you. So that was the proposal, and in particular, they had already done this. So looking over here on the computer now, put together a Datalog program. This is written in Souffle, which is an excellent Datalog engine, and it's a program, and we'll talk through some of it. It's going to essentially do the things that we just described, but it's doing them in Datalog. And we'll have to do a little bit of a mental shift to understand exactly how that's working. But Datalog happens to be, a language that's not at all bad at describing things like tree traversals and generally recursive interactions with data. And we're going to do a bunch of that, it turns out. There are some quirks, though, and Datalog has slightly difficulty expressing certain things. Mainly this is around the fact that Datalog is good at deriving facts. And facts, once true, do not become false, which is good. We like that. But sometimes it's important in designing efficient algorithms to hide information from the computer. And I'll show some examples as we go along. But this essentially led me to do a differential data flow version of the Datalog first, and then looking at the moments where there's some pretty gross computation that goes on for no particular reason other than that Datalog only lets you express certain concepts. Then I went in and sort of hotwired a few interesting moments using base differential data flow. I'll call these out too. And it got to a state where things were relatively prompt. This is the program. Let's see what happens if we run it with a single worker. I'm sorry. I have some diagnostics that I'm not supposed to show you yet, I think. So we'll rebuild it. This is essentially, so to spill the beans, I think I know what's wrong with this, and I wanted to confirm my hypothesis. I haven't yet fixed it yet, but I did want to make sure this wouldn't just be a super boring, like, oh yeah, I guess it's slow. Sorry about that. So this is the differential data flow program here, and it largely tracks, we'll start to walk through it in just a moment, but it largely tracks the Datalog program except for a few exciting callouts. This is an exciting moment, for example, where we use reduce, which doesn't exist as far as I understand, in Datalog. And yeah, great. So it took some amount of time, 2.5 seconds, let's say. It takes a little less than that so some of these printouts are essentially trying to track when certain moments in the data flow are complete. And let's hide them just for a moment. Oops. When I was screwing around with this before, it took just under a second, like 1.9 seconds or so. And this absolute times aren't crucial. It's not a bad time. It's not the best time. I looked at this again because there was an article in Hacker News where people were really leaning into trying to optimize this and getting it down to, I think, about a 20th of a second or something like that, which is pretty exciting. We're not going to try to do that, though we might try to improve the performance, in particular to improve it when multiple worker threads get involved. But I just want to get this to a state where we can see, it produces roughly what I was saying before. Great, good, running. Well, it's a little slower than before. Not entirely sure what makes these things slow or fast. It's probably not the right thing to hear before a session on trying to improve its performance, but let's continue on nonetheless. So we've got a program here. We have a Datalog dealie here too. Let's try to walk through the Datalog just to try to get everyone on the same page about what we're doing. All this stuff is in the repo if you want to check it out. I think that's a sane thing to do if you want to take a moment just to read stuff that I'm scrolling by pretty quick. The gist here, this is some of the stuff is sort of souffle-isms, so like we're building certain relations, the assign relation, the remove relation, the insert relation. There's some complexity I didn't mention, like you can add facts to the remove relation, and that basically just supposed to delete them. So if we didn't like the E that came after H, we could delete it after the fact. We can't actually remove it because other people might have based their coordinates essentially on that E, but we can add a new fact that says, when you get to that E, just delete it. Don't, essentially put a caret H right after it, which is, sort of a Datalog-y declarative way to talk about deleting a thing rather than actually deleting it. And this assign thing here is essentially that the actual letter doesn't have to show up in the core of this conflict resolution stuff. So these insertions come in and they don't actually have any data with them. They just say child and parent relationships. And once we figure out the order on things, we can go and look up all the letters and see what's actually supposed to be there. And for the bulk of this work, there's essentially no meaningful letters, characters assigned to any of these locations. The hard work is actually doing the conflict resolution rather than printing out the letters that happen to be associated with each of them. So the gist here is we're going to start out again, and we're just going to put together, this is some more souffleisms, I think, put together some structured relations, insert and remove from the input collections. And then we'll start doing some logic here, and this is where we start defining rules. So for example, we might introduce a new predicate, which is has child of parent, and a parent has a child if there's some insertion where we don't really care about the first field, but the parent shows up in the second field. So this is good. This will clue us in if a particular node has any children, and that will show up as useful in some bits of logic. There's some stuff here, and I'm going to have to scratch my head a bit because, to be honest, I struggle with some of these things. There's a pile of logic now, which I think sort of goes all the way down to like here maybe. That's essentially asking for each parent which child is last of it. So if a parent has 5 children or something like that, one of them comes last. And that's the thing that's very awkward to describe in Datalog. Essentially, you need to think about all possible children, and then think about for every pair of children, if you happen to be less than another child. So if you have a parent and child A and child B, if A is less than B, A cannot be the last child. You can do the same thing the other direction for the first child. But essentially we're doing some crazy reasoning here, producing what I would say are a quadratic number of facts, so parent and each pair of children, in order to figure out the sort of first and last child of each parent. And I don't know that I recommend paying too much attention to this. It's all a bit gross, and really what we're trying to do, if we look over on the tree here, is we're trying to put together a relation that is, for this H, for example, we want to put together a relation that says that HI comes before, draw it differently, comes before E, HE in particular. So this node comes right before this node. We want this because we're trying to put these things back into a total order. We don't want to have to bounce up through H each time to figure out, like when we're done with I's subtree, right? If we do all the work over here on the left, what do we do next? And the answer should be go do all of the E stuff. And we need a little bit of help in the form of this Datalog rules to try to put that together. So that's really what all this next sibling stuff is trying to figure out. And like I said, I'm not going to force you to read all of that. There's a much simpler version, in my opinion, that we'll see in the differential data flow version, where we just say, like, well, group all the data, sort it, and then read them out in order, which works great for me and is not quadratic in the number of children that a node has. So let's imagine that we address that. The two hard things are coming up, and those two hard things are the first one is this next sibling ancestor. So what we're trying to do, let's look over this tree again. We've got a node, and we've got various children of that node, and they have various children, and and it sort of continues. The awkward thing that we need to be able to do when we're reading this out, trying to read this out left to right, is to process all of this tree in here. Once we're just about done with it, we go on to the rightmost node here. We've got a little bit of work to do here. Once we've finished with whatever the last node is in this subtree, we need to figure out where to go next, right? There is no next sibling anymore in this tree. There isn't even a next sibling one level up in the tree, potentially several levels up in the tree. So what we're trying to figure out how to get to is how to draw an arrow to this node here, right? This is basically, if you climb back up the tree for as long as you are the last sibling in the list, and then once we finally get to a moment where you are not the last sibling, wander over and grab the ID of the next sibling. That's the next person in line. So we're trying to put together all of these pointers so that eventually we can read out just in one straight line all of the sort of the linear order on all of these edits that have gone on. So that's a little awkward, or at least that's what's going on in this rule here. Awkward is wrong, but it's the first time we're doing an interesting sort of recursive rule and stuff like that. So we're going to describe this next sibling ancestor. It's essentially going to try to do this climbing up the tree thing. So it starts with next sibling start, comma next, and this I believe has been hotwired to point up if you're the last sibling. And what we're going to do is, if you don't have a next sibling, then we are going to sorry, I might have lied about it pointing up. Let's see if we can figure this out. I apologize. So we've got a nice base rule that just says if you have a next sibling, great, just write that down, put that in there. Now, you might not have a next sibling, and in that case, what we want you to do is to figure out what your parent is. So we're going to go and say, like, okay, you don't have a next sibling, star. Let's go up to your parent, and let's figure out who your parent thinks is next. Who would go after your parent? So sorry, nothing points up to your parent other than the insert statement. Now, as you can sort of see from the picture, that might not have gotten the right answer yet. But we'll make progress to it, right? In the sense that this node here, this intermediate node, I'll give it a name, B or something. B, in one application of this rule, will look up at its parent and say, ooh, you have a next node. Let me just inherit that. I'll add a dotted line from B up to that node. And the next iteration, if this is C down here, C's parent is B, and so C, this rule will fire with the start of C. It doesn't have a next sibling. It does have a parent. The parent is B, and B now, after that first round of derivation, points at whatever this node is up here, maybe D. So that's great. And essentially, we will climb down the tree sort of repeatedly, as deep as it goes, providing more and more links to various children, various rightmost children, about the next nodes that they should go to. And almost certainly, what we're eventually going to do is totally ignore the links from B and C to D and just use the very last one, because that's not the one that actually, B and C are meant to happen much earlier if it's a preorder. And quite possibly this next elem does that. Let's see. So if you don't have any children, then we'll use this next sibling thing. Great, that makes a lot of sense. Otherwise, we'll use your first child. So this makes a lot of sense. It says for every node, if you've got a child, go there. Otherwise, go to the next sibling. Go to the next sibling. And because we just did that next sibling ancestor thing, maybe you bounce up a few times and go over to a node somewhere, as some sibling of one of your ancestors. Yeah, great. And that's now the next elem relation. This is, I think, a nice semantically meaningful relationship that sort of tells us, for this tree shape thing, what, let's sort of draw it in here, what is the order that you're meant to follow. And it untangles your potentially complicated edits into nice linear order that is just going to be what you present. And it's a nice recursive bit of Datalog, sort of thing that differential Dataflow is meant to eat for lunch. We'll have to see. And then there's another complicated thing that goes on. So that's a bunch of the work, like a bunch of the hard work has happened now, though there is actually some more stuff to do, it turns out. You can sort of see it here, assigning values to list elements. And you might think, great, we'll just go and look up the values. There was this assign relationship, right, that said something, for each an ID and an element, I think the pair together make a unique location in the graph, maybe. But what do we put there? And you can sort of see that, like, yeah, great, we'll just use whatever's in assign as long as there isn't a remove. Because if there's a remove, we're supposed to delete it, right? Yeah, that's true. Well, there's a sort of annoying thing that happens now, which is that you don't want to show everyone all the removes, right? Like, you don't want your document to be full of a whole bunch of, I don't know what it would be, spaces or who even knows what. We're supposed to have deleted a thing, and so you're supposed to present it as not there, not just there, but not visible or something like that. So the next thing that happens is some logic that goes through and does this skip blank stuff. And the goal here really is to say, we're going to totally imagine, we fixed this tree thing now, so we just have a linear order. Like so. Some of these might be X'd out, like they might be dead, because they were put into this remove relationship. And what we really want to do in that case is change the things that are dead are not edges. I apologize. Let's imagine that thing is dead and that thing is dead. So these two nodes here. We really want to update the pointers to skip the dead things. Just to say, like, you're of no use to us. You're not helpful from the point of view of showing off what's in the graph. We don't really want anyone to go in there and start screwing around with those records because they've been deleted. I don't know if it's not actually a requirement, but like for various ergonomic reasons, this is part of the program definition as well. So we're going to try to figure out how to skip all of these blanks, I guess is what they're called here. And the way we skip blanks, I guess, is as follows. So we go from and to, but we're also willing to skip if some intermediate node via has no value, right? Has no value because it was removed. I think that's probably the only way that has value can be false. Then we're also totally comfortable to take a next elem from to via and then via to 2 and just say, you can go straight from to 2. Don't even bother with it. I mean, via exists, but like, just skip it. And that gives a whole bunch of edges, actually, more than you might have thought. So it gives all sorts of little edges in here from every position over any sequences of edges, and then we basically just delete any edges that happen to end up at one of these dead nodes. Just throw them away, and you're left with only the big steps that go across. And that's it. There's like a little bit more, I suppose, about producing the output so that we can all agree that we've done all the work we need to do. You can check the output and see the answers are correct, I hope. And that's the Datalog program. So two pretty interesting things, I would say. This unfolding of the nested tree structured thing into a straight line, and then the collapsing down of these blank regions. Both of them have some warts, and I'll try to talk through now the differential Dataflow version of this that we wrote up. It's still got problems, so this is the thing we have to fix. We're still doing setup at the moment. So if we bop on over to differential Dataflow here, this is 150 lines or so. A bunch of it, down here. This is all just pushing. This is at the bottom. Sorry, pushing all of the data into the Dataflow computation. I tried to keep fairly similar names. They're not always the same because sometimes we just delete some of the rules because they're not helpful. But we have, insert, remove, and assign, stuff like that. We have it has child. For various ergonomic reasons, we occasionally want to switch some of the relations around. So sometimes we want to have the inserts keyed by parent, because we're going to want to maybe group them by parent. For example, all that horrible sibling stuff, for example, where we had to, this is the stuff that I just skipped and didn't talk through. It's relatively easy to say, well, let's take all of our inserts grouped by parent, do a reduce on them. So this puts all of the children together, for each parent, all of its children together, in sorted order. And then we just produce an output that says, for, essentially, for the children in sorted order, if you have n children, produce the n-1 links between them. So from each position I to i-1. So this essentially puts out a comma b if a comes just after b for some arbitrary ordering. It happens to be the Rust order on these types, but you could make it something more interesting if you wanted to. You could just call sort on input if you wanted something else, for example. This then, we sort of figure out next siblings and first childs and stuff like that are potentially interesting and exciting. Has next sibling. These are, I don't know, they're now analogs of the Datalog program. I'm not sure if they're exactly the same. Like there's some question about whether you go big to small or small to big, but in any case, we then reach the next sibling ancestor computation, which we're going to model as an iterative differential data flow computation. That makes sense. There's a little comment here that says that we're doing this using iterate because no mutual recursion, and I think all that I meant there was that Datalog potentially allows mutual recursion. You can have multiple relations that refer to each other, and iterate by itself is not really powerful enough to express that without some really gross hacks. You can do it in differential data flow, but if you have something as simple as just single recursion with no other variables, then little pixie poo there. Then you can just use this iterate computation. So I think that's all that I'm saying up here. The first time I read this, I thought this was like, oh geez, was this a restriction, or did I do something wrong? And I think it's just a matter that it's easier to write, easier than is strictly required by Datalog, or Datalog could require. So anyhow, the algorithm, or the iterative computation, I believe, we'll explore it together, parallels the code from the Datalog. We grab a copy of the inserts that have gone on, we grab a copy of has next sibling, and we grab a copy of sibling. And these are all just, we need to pull them into the scope so that they can be used inside this iterative scope, even if they're not evolving. We do need, we plan to use them, and we do need to pull them in so that we can use them. Ignore this for the moment. This is just me reporting on some information that's going to be relevant pretty soon once we try to figure out why this is potentially slow. And what we say for each iteration, so the way iterate works, right, is you start from some data and you give it a closure that says, hey, whatever your data are now, I would like them to become then whatever this closure evaluates to. So for any current set of next sibling ancestors, we're going to make it be equal to this next time around the loop. All right, what does this mean? So we're going to insert followed by an anti-join of has next sibling. So we're going to delete from insert all of the insertions that have a next sibling. Sorry, all of the children that have a next sibling. So I believe what this is going to do is just leave a straight line up the right side of each of these trees, more or less. So this is going to tell us about the people we need to fix, in some sense, the folks we need to go in and add in. Once we've gotten that, it's in the form of sort of child comma parent. We're going to swing it around to be parent comma child, because when we do a join, we need the key to be in the first position. This is a quirk of differential data flow that it sort of explicitly requires you to put data in a certain form. Datalog does not, makes it a bit more terse. That's sort of nice. We're going to join this now with inner. Essentially, we're going to say for each of these children that don't have a next sibling, grab their parent and go look up their parent in the current next sibling ancestor. Sort of, and we talked through this before, but essentially we're going to do the same thing of like, go and ask your parent what they think the next sibling will be. And great, once you know that, just ignore the parent and write down the that next target. And make sure to add in the next siblings. So we actually want these edges that go sibling to sibling. Those are an important part of actually getting to the right answer. They're not going to evolve iteratively, but we do need to put them in there. And then we have the whole thing with the distinct, just because this is good practice for iterative computations to make sure you terminate. It's not immediately obvious that we would risk deriving facts multiple times, but best to avoid that problem. So this is an implementation of this next sibling ancestor recursive relation that we saw previously. And this will be one of the interesting moments when we try to fix the performance. And I'll try to explain why when we get there, but just sort of walk through the rest of the stuff. This next elem relation, you might recall, we put together, and this is the linear representation of all of these updates. So we take the first child of each of the parents, and we add to it the next sibling ancestor relation, where we delete anyone who actually has a child. And I think that's basically sort of verbatim. So we take first child and we concatenate anything in from a next sibling ancestor except those folks that have children. Great. Yeah. Now, some more stuff happens. This is basically fairly similar to what we saw in the Datalog. Up to this point here, we're really interested now in deleting, essentially removing these paths of the form blank star. And this is one of the changes that I made. It's a Datalog to Datalog change, so you could totally just make this in the original Datalog program. It seems like a good idea, which is that we don't really want to compute all of these paths of the form blank star because there's a quadratic number of them, right? If you have a path of length 1,000 that has all blanks along it, you kind of just want the one the one from the start to the end. You don't want the one from position 317 to position 732. Like, that's not a relevant subpath for you to know about or to even bother to compute. So what we compute instead of paths of the form blank star are paths of the form, highlighting it properly, value followed by blank star. So we restrict our attention to just starting from actual values, so non-deleted values, and iterating forward from there. And like I said, you could totally do this with the Datalog program. Other people have, and going forward, people just should. So not a big change of consequence. I mean, it certainly helps out the computation, but it's not. This is not the reason anything was slow. We're just gonna do the same sort of thing again. This is just an iterative exploration of this relation. So we start with something that is a value. So this is the next element semi-join with has value. So this is next element steps that have a value. Yeah. And we're gonna start from that, and we're repeatedly going to follow a blank step, essentially. Follow a blank step, and we're gonna concat back in the value step to make sure that we are growing our set of facts rather than only looking. So we want to make sure that the star can be empty as well, so that we reach a fixed point. We want to keep our base case in the collection that we're iteratively developing. Great. And then basically we're done. I mean, the rest of the stuff is putting together the results to sort of show them to you. Or, sorry, just to be honest, just to make sure that we're computing the right results, or checking it against other systems, checking it against Soufflé, for example. Great. So that's the whole computation there. And there's some data that comes along with this, which is what we were running before. This is data provided by Martin, and supposedly it is something that he captured while typing some document. I have no idea. But if we look at it, so if we look at the inserts, for example, they're just a bunch of, a whole lot of like child pointing at parent, 4 points at 3, 5 points at 4, 6 points at 5, 7 points at 6. You might conclude that there's maybe more structure that could be exploited in here. We're not going to take advantage of that here. That's a totally legit thing to think about, to say, like, why not just insert words at a time, or that sort of thing. People have brought this up before. That's a great question, and I am just here to optimize the computation. I'm not here to try to invent a new algorithm or anything like that. So we saw how long it takes to run. It takes 2 seconds or something like that. There are, let's see. There are a whole bunch of lines in insert and some number of lines in remove. So I don't know, you add these things together, you get 250,000 updates, or facts that need to get handled. So actually that's pretty simple. I think that number, if we take this to be 2.5 and these things to add up to 250,000, that's something, 10 microseconds, is that right, for each fact on average? Which is not the right way to try to figure things out, but if that's right, yeah, I think so. If that's right, then I don't know, 10 microseconds sounds like a small number, right? It's not great, it turns out, but it's not terrible either. You could easily waste more than 10 microseconds in some other frameworks. So let's get into what the problem is here. I have a few little things that I have put in various places. These are going to be hard to read. Let me uncomment it and sort of format it a little bit better for you. So this is just a data flow fragment, though it's really not even a data flow fragment. It takes a collection and deletes its data and says, like, I don't care at all about your data. I just care about knowing that you're done. Consolidates the data. Consolidate happens to wait until it's sure that it has the right answer before producing a result. When it does produce a result, we pass it off to a map here that is going to report both how long it took to get there and also, I guess, how many records there were there, which is helpful potentially. And the real problems, I'm going to spill the beans right now. The real problems are here in these loops, and we'll see why in just a moment. So this is next sibling ancestor, and we're going to steal the same thing for the next loop down here. This is value blank star. So let's run these things. Let's see if these run actually. And we're looking for, well, you'll see it. It'll be unavoidably obvious actually. And I'll try to explain or interpret the results for you once we see them. All right. Well, there's a lot of stuff printing, isn't there? So this is the problem, and the problem is, even though we might have liked these loops that we described, and even though we made them linear instead of quadratic or whatever, this value blank star thing has to iterate 14,000 times. So there's some path, this is my understanding, some path 14,000 long of deletions that we have to go and chase down. And that just takes time. I mean, this is a thing that differential data flow is not brilliantly optimized for. It does do iterative computation, it does them relatively fast, but each time around an iterative computation, it takes a little bit, like there's some synchronization that needs to happen, there's some coordination, or we need to make sure that it's appropriate to continue or not continue. It's much less efficient than a for loop is. So like a for loop that just sort of grinds through some data. Nice data parallel action. We just go into all the work, and in principle could spill that work across a few different worker threads. This is also a loop, but it is a very sequential loop. We have to do all of these rounds of derivation because they each depend on a prior round of derivation. And so we can't really parallelize them, at least not in differential data flow. So that's basically the heart of the problem here, is that in fact there are so many rounds of these things that it blew the buffer, and we can't see that there's, for the next siblings ancestor thing, there's about 7,000 rounds of derivation that go on there. So that's also problematic. There's some long path, 7,000 long, that you have to climb back up to figure out who's next. And that kind of makes sense if you look at the picture here, right? Like if you and I are each typing and I'm working on my chapter and you're working on your chapter, for you to finally figure out, once you're at the very end of your chapter, where do we go next? You basically have to walk up all that text that you typed. And there's a lot of iteration to go there. I mean, it might be 7,000 characters that you typed in a row. It really, in a perfect world, in fact, this data structure, although it could be a tree, probably looks like a whole lot of straight lines. Right? Like that means there's not much conflict. That's great, actually, from the point of view of minimizing conflict, but it's pretty terrible from the point of view of climbing back up these things in small numbers of iterations. So that's too bad. Yeah, and this time actually, to be honest, seems surprisingly good to me for something that has to iterate 14,000 times. If you thought about, how fast am I restarting around a computation in this? If we're okay, these numbers went up because we printed out a lot of stuff. But if we were saying that this takes 2.5 seconds, and we did 14,000 things, I think that means that in less than a millisecond, we're going around rounds of iteration. Each round of iteration takes less than a millisecond to do, and you sort of compare that against other big data frameworks that would need to do something much more heavyweight. Now, of course, the data here are tiny, so like don't think too hard about other big data frameworks and whether you might use them. But yeah, this is the heart of both. I think we'll find out because we're gonna try to fix it, and if it fixes it, good news. Both what's slow and also what prevents parallelization. Because you can also see this last term is the number of records. So one, basically, like there's all of these rounds of iteration, one thing happened, one fact, and then one more, and then one more. And it's exactly like you might imagine from what we've just sort of seen looking at these trees that are largely paths. It's not too surprising at all. But you can absolutely see that there's no way that invoking 8 threads to help do that one thing is going to work out well, and we can't in differential data flow get parallelism across rounds of iteration because you need to wait for one round to complete before you release the data and start working on the next round. That's not, by the way, a property that Datalog has. Datalog can, in principle, parallelize across rounds of iteration because it's monotonic and does not, like as soon as you know a fact is true, you can hand it to someone and they don't have to wait for the rest of the work to get finished. But let's talk through how I think you can fix this. I'm going to go back to the picture board over here. Here is our pictures, and remember that one of the things we're trying to do is climb up the, my ability to draw nice thick lines has gone away, climb up the right-hand side of some trees. Probably, to be honest, probably just a long list, but yeah. Now, what we had been doing is asking each node to sort of go one step sorry, to figure out its neighbor, go one step up, look for a neighbor, one step up, one step up, one step up, one step up, step up. And that's only ever going to get us a linear number of iterations. Though we can try to do something smarter, right? We could, instead of having folks, this will light up nodes sort of in order going down the tree, like so. We could instead ask folks, why don't you get a head start? Why don't you, while everyone else is actually talking about this one neighbor over here who's really exciting, why don't you start taking multiple steps up the tree here, right? You know your length 1 path, why don't you form a length 2 path in the meantime, then maybe a length 4 path. And generally speaking, why don't you form the longest path you can up to a node that has a sibling, right? Like you don't want to shoot past that node, of course, right? So everyone, if we sort of zoom in here, everyone over here on this right side of the tree can look for a node, it'll be this node, but a node that has the property that it has sibling, I hope. We'll figure out which predicate it is. But essentially we want folks to climb up until they get to this point. And we won't overshoot it because we won't have that edge ever in the mix. And the gist here is that because everyone's going to start doing this repeated squaring type stuff, the number of steps we should take should end up being logarithmic rather than linear. The downside is that we might end up doing an amount of work that is n log n rather than linear. Right? Each of these nodes will probably, in the course of things, derive log, if n is the depth, so d, let's call it, they'll probably derive log d facts about themselves, log d different ancestors that they would pass through on the way back up. So it's a bit more work, but it's a dramatic reduction in the number of iterations, and it's also substantially more parallelizable, which is really nice. And yeah, so that's my plan, at least for what to do. Let's talk about the plan for the other thing too. The other problem, the deleting of the value blank star thing, where we have nodes. Some nodes have value, and then we have potentially a whole bunch of nodes that do not have values, followed by someone has a value, followed by value. And our goal is to figure out how to get to that instead, that one long edge that reaches across there. And we're going to do the same thing that we did over here. We're going to try out repeated squaring. And the gist here, actually, we're going to do a little bit of a regression, if you will. So where we had said this was value blank star, meaning start from a value and only start from values. Don't start halfway through because that's a waste of everyone's time. Yeah, we're going to start at various points halfway through now. But instead of figuring out all of the various links that might exist in here, we're only going to have folks take these power of 2 size steps and make sure that they halt once they get to an actual value-bearing node. And the gist is, again, this might end up doing, will end up doing a logarithmically larger amount of work, but only take a logarithmic number of rounds. And again, the hope there is that cuts out a substantial amount of overhead due to total amount of iteration, and makes the work substantially more parallelizable, so that we might be able to turn on multiple threads and improve the running time. And I don't actually have a good sense for whether on one, well, we'll find out, but whether on one thread we should expect this to go any faster or not. If we're keeping the same amount of work, if we're holding that constant, then yeah, definitely doing fewer iterations is a lot better. There's a bit of a trade-off in that we're causing more work to happen, but by removing the overhead of the iterations, we're probably improving the efficiency. We'll have to see. All right, so I haven't tried to write this yet, so I'm going to try that now, and we'll see what happens. But I thought we might start, since we've talked about it quite a bit, we'll start with this has sibling stuff, this next sibling ancestor logic over here. And we have to be a little careful because we're trying to do something that's a little bit sneaky, and it's easy to accidentally screw this up and potentially compute far more results than you actually want. So, for example, although we're starting with these sort of single steps going up here, we want to forget about them pretty quickly, meaning that once we've, after our first round, everyone will have a length 2 path, except for the last person, but that's fine. When we next think about where do we go from there, we want everyone to join length 2 paths with length 2 paths, roughly. We don't want to use these length 1 paths anymore because our goal isn't to fully populate all of, we don't want length 3 paths going up there. That's a waste of everyone's time. We want essentially a path whose length is the either a power of 2 if it does not arrive at the target. Either a power of 2 or, if it does not arrive at the target, a power of 2, otherwise whatever the correct answer is to arrive at the target. And we don't want these little dopey things in here anymore. So we actually want to use one of the nice properties of differential data flow, which is that its iteration can be non-monotonic. That is, we can discard those short paths after each iteration. And the easiest way I could think to write this down was to track the length of the path, essentially, at the same time. So if we track not only, if we think about child, parent, and then, I don't know, length or something like that, where all of the paths start at length 1, we do a join between these two, whatever, our iterating quantity. We do a join between that and itself. And then for each child, we maximize over lengths. So we pick the parent, parent is wrong, ancestor. So we pick the ancestor that has the largest length, the largest distance away. So that will keep us growing, and everyone will be growing by factors of 2 each iteration until such a time as they find an ancestor who actually has has a sibling. So let's try that. I need to get my coding hat back. I had my explaining hat on for a while now, and I need to actually think about the right way to type this in. So we're gonna rather than concatenate in next sibling. So these are the base facts, right? Rather than concatenate these two things together, we're almost certainly going to take inner and join it with itself in order to make progress along this thing. Let's actually, before we do that, we need to do, I think, one other little transformation here, which is we don't just want to start with the next sibling relationship. We want to we want to be a little careful here, because we don't want to step the next sibling relationship, if you recall, also includes like all of this crud, right? And we don't really want to geometrically race along that or anything. I mean, we might want to. That's a good question. But as soon as we've taken one next sibling step, we stop, right? So we're sort of keeping it around out of convenience, not because we actually want to do this ascending racing around on. So let's think through how we might want to restructure this. I believe that we want to, in a sense, probably start with this. So starting with the insert anti-join. So these are the insertions that don't have a next sibling, right? So the folks who are at the right edge of the board. And the main goal here, I think now, is to just race up this relation. So if we draw a different picture here, if we try to draw these edges, they look like those edges that go up the right side of a tree. And as soon as they reach that node that actually has a sibling, yeah, they stop, right? Because, well, it has a next sibling, and so we did not include an upgoing edge from it. We want to be a little careful here, because we Oh, maybe this will just work out, actually. I was going to say, often you want to put a little loop in here so that your facts don't fall off the, if you do a join and you don't find anything there, that sucks. You actually want to make sure to reach this instead of, forming an edge to it and then trying to do one more join and just not having a fact be produced. But my guess is that maximization we're going to do each round, where we take, let's say, our prior paths, our new paths, and give them the longest length, we'll probably keep around all of the information that gets us to there. So I think we just want to start with this insert anti-join. Let's start writing up here. So insert anti-join has next sibling. The typing is going to be hilarious, sorry. So we're going to just basically collapse down these paths to find the first ancestor that does have a next sibling, and that's really our only task. And we'll put together the pieces afterwards, like figure out what it should point at. It should point at that sibling, of course, but we'll put that together with all of the other next sibling relationships. So we're going to iterate. Probably give this a name. I have no idea what to call it. Great, we'll call it ancestor with next sibling, because naming things is an important part of staying sane when you're trying to many sources of complexity already present here. So good. So we've got we've got a bunch of pointers from children to parents. Let's actually change this a little bit and say child, parent. We're going to give it a length also. Length of 1. And this is going to be the thing that as we increase these sets and their lengths, we will maximize over that number to try to keep the single longest edge that we can find. So we have a whole bunch here in inner. We have a whole bunch of child to parent with length. We're going to want to restructure these so that we can join them. In particular, we're going to want to, let's see if we can just write down the Datalog rule. So if we have an ancestor with next sibling from, this is a bit, sorry, I take that back. They don't actually have next siblings yet as we are evolving them. So this isn't the right thing to call it. Ancestor without next sibling, I don't know. Anyhow, if we go from child to Inc1, L1, and ancestor with next, without next, we'll write it down and see what happens. So here's the intent, which is whatever this relation actually means. If we have a link from some child to an ancestor or some length, and another link from that ancestor to another ancestor with some other length, then we can put together a link of the sum of their lengths. And I don't know the right way to describe it in Datalog. We're going to only want to keep the largest one of these, so we can just write it in differential Dataflow though. So we're going to want to take this inner relation and organize it both by essentially we'll put it in joinable form, both the relation and its transpose. So we want to do inner one, I guess we'll call it. Inner.map, I've got the child, parent, and length. child ancestor in length. And we'll put that as ancestor and then child comma length. So differential data flow very much asks you to put your data into a key value form. So this is the key, this is the value. Instead of leaving them as flat triples, in which case it can't tell what's the key, what's the value, and what's the third field about. So things need to be pairs if they're going to go into a join. So here we have a C, an A, and an L, and we're going to do C and A comma L. So this is essentially the first version where it says that if we've got, we're going to look at going from this child through this ancestor. So with the use of the first relation here, we're trying to key it by ancestor 1, so that when we do a join, we'll get out child and ancestor 2. This is the child, this will be the ancestor 2 that we're looking for here. So let's join those two things. Let's do inner 1.join, inner 2, join map probably. Join map allows us to apply some results to the key, which we don't care about. This is the middle, the via, if you will. And we have I'll write it out because I like len1 and enc2, I guess. I don't know. Len2. So you get to write a low closure that is the key, the first value, the second value, and then what do we want to produce? We want to produce, I believe, child, and then enc2 comma len1 plus len2. Now, having done that, so this is a bunch of facts that are of the form, this child can reach this ancestor in this many steps. We want to do a reduce here to grab all of the facts we know about children, this child here, sorry, for each child, look at each of its ancestors and basically pick out the one that has the biggest length. And one way actually we could do this if we wanted to would be to put these in an opposite order. Let's not do that just to avoid the complexity. You could put them in the opposite order and then they would be sorted and you just pick the first one. Instead, I guess we'll scan through them. Blah. Let's do this. Great. So the reduce operator asks for a closure that says here's the key. So we're going to go group by group. Let me show you the key. Our logic isn't going to depend on the key at all. You have to read from the input right to the output. And we're just going to essentially take the last input. So it comes in the form of a value and a weight. Like how many times do I think we're only expecting to see each fact there once, but in any case, we will don't really care what the weight is. I forget if last is actually a thing, if we need pop or what we need, but let's so we're going to push in length, ancestor. We need to do the same thing, by the way. We need to put a weight on there to say essentially how many copies are we producing of a thing. Differential data flow is multi-set based. So we could put 5 copies in the output if we wanted to. We don't. In Datalog, usually we only need to put one occurrence of a fact. Anything else is sort of distracting. I think we're probably going to need to put some stars here too. These come to us as references, and we're going to just need to dereference them so that we don't try to push references into the output, and that will super confuse Rust and differential data flow and everyone. Great. So I think what we've done here now is iteratively develop these edges that go from nodes that don't have a next sibling up through their parents, terminating at whatever, there's some node up, that was the last one in the sequence that didn't have a next sibling, just sort of ends there, right? There's no edge coming out of it in this collection. And I think we'll just keep looking for those things and keeping our hands on the biggest one. And yeah. So this now tells us for each node which ancestor it should essentially look for. Whose next sibling should it steal, right? And if we look down here, I'm gonna comment this out just because we don't want to accidentally do it. But if we look at what goes on in next elem, right? There's first child. What does first child? It says if you have children, don't use your next sibling, right? Because you're going to go down. And in a sense, what's happening is that next sibling that you could have used, we're going to hand that to whoever in this iterative process wants to steal it from you, in essence. And let's try to find the right way to write that. There's a lot of crud in here, isn't there? I'm going to steal this up above just to be a little closer so we can track this and make sure we're using the right concepts here. So we want to produce all of the next siblings. Those are the horizontal edges, except for those folks that have, essentially we'd like to pull out the next siblings for people that have a child. Put those aside. We're not going to put them in as written. Instead, we're going to overwrite the source of that edge with whoever wants to go and steal it from the person. So let's see if we can write that, which is next sibling to take. So these are going to be the next sibling dot semi-join, I think, has child. So I think this is going to take the next sibling relation, which is a bunch of child comma child relations, and this is going to keep only those of folks that have a child. And particularly, we're not going to use these. Like we don't want to put these as they are into the output. So what we want to produce as next elem, then I think it's going to be. We'll probably have to rewrite this for clarity. I'll have to rewrite the whole thing for clarity, I'm sure. But so we're going to want first child. We've always wanted that. This is the thing that points down. We're going to want to concatenate to this. How do I write this? Concatenate to this. The edges going across that are not, so the next siblings, except for next sibling to take. So that will be, this is a bit weird to write, but I apologize. Next sibling to take dot negate dot concat next sibling. So what have we said here? We're going to take the first child, we're going to add to that next sibling minus those things that we're planning on stealing. Right, so this is the way that we, essentially this is the anti-join in here. This is, don't put into this pile the next siblings from folks that do have a child. And we'll also want to concat into here a join now between ancestor with next sibling, which probably doesn't have the right structure yet. Actually, we need to figure out how to delete the length or just ignore the length. This is going to come out as a length comma ancestor, and we really wanted it to be an ancestor comma length. I'm not sure if we really needed that, but let's change the order just to try to avoid. I think ancestors have a different type than lengths, I hope. All right, so now what comes out should be what comes out of iterate is always the same type as what goes into it once it compiles, which should be keyed by child, the ancestor, parent here, but the ancestor that we're going to steal from, as well as the length. And we're going to need to spin that around because to actually look things up into this next sibling thing, we're going to key it by the ancestor. So let's write this out as ancestor with next sibling dot map of child ancestor. We really don't care about the length. We'll turn that into ancestor comma child so that we can do a join. I have my parentheses wrong. So we can do a join with next sibling to take. Join map, let's do. Which will have the ancestor, which we don't care about. We're gonna, the first thing here will be the child, and then the sibling. And our goal is to produce child comma sibling, though probably with some dereferencing that goes on. And we need to put a little ampersand in front of that for concat to work. Now, I mean, it's probably wrong, but like I think that's a good first stab at what we're computing here. You know what we should totally do is we should just leave this around, of course. We don't need to get rid of it. We might get rid of this. But ideally, this produces exactly the same result. Like for it to be correct, we want it to produce exactly the same result. So let's do that right here. I believe that there is two next elements. Oh, I stole it and I changed it. Okay, hold on. Put this back down here. This will be next element. This one up here can be next element 2. We're not really interested in switching over to the new implementation until we're comfortable that it's so this, unless it's a different method, we'll have to see. There's a method on differential dataflow things that asserts that two things are equal. Two collections are equal by essentially consolidating them. That's subtracting one for the other, consolidating it, and making sure that there is never a diff between the two. It should be pretty noisy if they're ever not exactly the same. So let's see if this checks. So there's for those of you who aren't familiar, there's now a long process in which we figure out what in the world has gone wrong with the types that we typed in, and usually it's some ampersand somewhere. Sometimes it's much more catastrophic than that, but for the moment, let's be optimistic and hope that we just need to type some ampersands. All right. Oh, this is good. That's just an ampersand. We've got some other errors up here. Sorry, I'm going to make this a little bit smaller so that I can read it now. Hopefully this doesn't screw up your readability as well. Oh, I have to... Sorry, apparently there's some errors in some of the other projects. No idea why. Great. So we have here... Okay, so we changed the parenthesization of these things, but we did not change the use of it. In fact, we didn't have to here. Well, we can tidy that up in the future, or we can just leave it for clarity. Oh boy. All right, so this method exists, but blah, blah, blah. So the giveaway here is that there are some references to types, and that usually means that we screwed up and did not dereference enough. So like, for example, this last thing, let's just say pop instead. We got to pop from, no, that wasn't good enough. Maybe we'll leave on last. Last probably returns a reference these are now references to references, and we need to figure out the right way to unpick all of that. Yeah, this is unfortunately not a very helpful error message. I think all it's really telling us is that somewhere in here we have references to IDs of things. This one, I would guess. let's just try putting another star in front of it. There's some world in which it's really not loving it, is it? It's oh, sorry, that's not the problem at all. I apologize. We have to do the same thing up here. So join also hands back. Great. So let's give it a run. I entirely expect it to error out and say that was not a correct transformation you just did, or we computed some slightly different results, and at which point we have 250,000 facts we might have to flip through to see where the screw up was. But hopefully we'll figure it out. I think, forget if assert EQ tells you what the difference is or not, but we'll see. And if it doesn't, we should just fix it to do that. I think we still have some horrible printing going on in our loops also, which we'll have to survive. Should we get to a point where things are correct, I'd love to put that same printing thing inside our loop to see, hopefully, that it takes substantially less time than, or substantially less, fewer iterations than before. Oh, right. Yeah, okay, so it reached a different conclusion. It concluded, for example, that 569 should point at 479. I think these zeros are the tie-breaky terms. They're not super relevant. I think it's just telling us the first screw up. It's not telling us all of the screw ups, which is too bad. We could fix. Well, sorry, we could start with this, but we could also fix the assert EQ method, because it does a consolidation, which means it produces a batch of data, and it could just report the entire batch at us, which will show us all of the diffs instead of just the first one. Just gonna check its implementation to see if that's actually what it's doing, so that we assert empty. Right, so assert empty, sorry, does a consolidation, but then lowers it back to a stream and just asserts on the very first record that it sees. So all that we really know over here is that this one record was in difference. We could certainly print out all the diffs between the two of them. I think that's an easy thing to write. Let me comment out, since we're going to rebuild this thing, comment out the other spammy thing there. And we can now try to get our heads around how, well, let's see. Here's some impromptu debugging we're going to do. I'm sort of curious to see how big these two relations are. We've computed the same thing twice. Sorry, not the same thing. We've tried to compute the same thing twice using different techniques. So this ancestor with next sibling isn't necessarily going to be the same size as any other quantity out there, though we could look at the two next LMs and see how big each of them are. So let's do that. So we take next LM, we say we don't care what your data are, we consolidate you, and then we can do a little inspect on the actual diff itself rather than kind of, sorry, let me check. I forget what inspect does on differential collections. Oh good, it just does the, never mind, we can use the differential inspect in this case. It will actually show us the right guts. And we want to do this for next element 2 also, and have it print a different string. And we want to comment this out for the moment. Should be, sorry, should be fine because we're not using next element, so nothing else is going to go off the rails. Ooh, we could also, sorry, kill this. We could subtract the 2 and consolidate and see how big that is. So we could do next element dot negate dot cat next element 2 consolidate, basically all this jazz again. And what this is going to tell us is just, you know, approximately how wrong are we, which I'm just curious to see. My guess is there's no reason to think if we're a little bit wrong. There's no reason to think we're just a small amount wrong. We're probably pretty wrong. So if it's only 5 records in difference. Ooh, if we made assert empty take batches, then yeah, it could be smart. And if there's a small number, like, you know, take an optional threshold or something. If there's a small number of errors, to show you what they are. And if there's a big number, tell you how many there are in error, which has an appeal. Or right at this moment, I wish it did that. Oh, I did actually print the difference. Did I print so much of the difference? Yeah, I did. I printed so much of the difference that I couldn't see the actual numbers. Okay. Do it again, and we'll just count the number of things in difference rather than... What you'd love to have on hand here, and this is definitely a situation where a sort of interactive shell, like a SQL-like thing, would be handy, is in sniffing around for the problems, seeing how many things are different between the two, and seeing if that's like roughly the same size as, you know, what, next sibling or something like that. Like, you know, if we just left out some fairly dumb sort of thing, well, you know, we should have been able to sniff that one out. I wonder, this seems like this is more complicated than what I did. There's a whole bunch of extra things. Inserts has next sibling, next sibling. I wonder, it's iterating on a bunch of these things that also just don't change, these sideways edges, which seems like, it doesn't really matter, but like having them in the loop seems a bit pointless. All right. This is actually, this is not. This is not great because all this number is really telling us is just the difference in the number of tuples, because we throw away the data and then consolidate. We might have wanted to consolidate and then take each of the numbers and make them, you know, don't just add up plus and minuses, because. All right, so we didn't drive as many things. If nothing else, we're just missing some stuff, all right? Which seems a little interesting. I'm trying to think if there's some good invariance here. Like the way that I just said everything before, the size of this thing should be, in essence, the size. I think the size of the has-child relation. What we're computing here, the size of the has-child relation plus the size of the next sibling relation. Because every next sibling shows up as an edge, possibly overwritten, possibly not. And then also we have the first child edge. So let's see, I'm just going to throw out some of those numbers too. Next sibling, and first child, or has child. Oh, I think this should be the same, right? Let's do has child too, just to... It's very possible that I give some names to these things that don't make any sense. So that size is sort of, I think, more clear to see in this framing. Could still be buggy, but more clear to see in this framing where we find these shortcuts and then piece together the results we want. And this one is a bit more, sort of continually build up various I mean, there's a logic to figure that out here. Like next sibling, anti-join has child is like trying to cull out some of the edges just before we put it in. So like don't put in any of the edges halfway up one of those paths, stuff like that, which I don't know, probably works. But all right, so these two numbers are the same. That's great. Next sib is quite small. That makes sense because siblings only exist where there are conflicts. And it looks like we have, if we compare next lm2, it's just barely bigger than has child, which seems wrong. Like we thought that it should be these two things added together, which if you add these two things together, you end up with a 5, which is sort of, I think, what we're aiming for. So is it a 1.5? It looks like it's a 1.5. Yeah, so looking a lot like the old version is correct and the new one is not. That's super believable. But since I just claimed that it's so much more interpretable the second time, we should try to figure out why first child plus... so here we're doing all of next sibling minus some stuff, and here we're doing this join with next sibling taken, and I guess what must be happening is this must be missing, right? So let's give this a name. So substitutions is going to have some size, and what we were really hoping was that it iterated up to child, ancestor, and we went back to an ancestor, and then we joined it with this thing, and we were really hoping that substitutions, I mean it's not apparently, but like hoping that substitutions had the same size as next sibling to take, right? Like we were hoping that everyone that has a child ends up with that child or some descendant of it, exactly one descendant of it, asking, hey, who comes after you? Based on the numbers we saw before, substitution seems like it's probably tiny, just because there was very little. So it felt like there were a few hundred at most records that got, well, in addition to the next sibling relation. Did we not? It's potentially empty. I mean, that's that's one reason that we wouldn't see a result printed here at all. Next element 2 is this. Ancestor with next sibling to take. Just a moment. Sorry, let's. First child that can cat. I guess we need to figure out how big this thing is. Do. Oh, wait, no, did we? Ideally, there were I suppose there is a smaller input data set that we could try. Or, if we think, for example, this is just screwing up. It seems like it's screwing up pretty significantly in the sense that it's not finding most paths up these folks, or not doing the right thing with them potentially. We could probably snip the data down to pretty small, to a point that we could actually look at it and say, like, where did the screw up happen? Now, what's going on here? Are there literally no... Oh no, it's just doing them out of order, isn't it? Well, this is pretty incriminating, right? The gap between these two things is exactly this size. There's some science for you. So somehow, the next siblings, basically it seems like the next siblings to take, which we're supposed to drop a whole bunch of records in based on that. It's not happening. Which almost certainly means, we can sort of see here, that substitutions are just utterly failing. We didn't successfully line up these keys, I suppose. Let's double check to make sure that we haven't done something very, very silly. But ancestor with next sibling, we decided was child, ancestor, so we spin that around to be ancestor, child. Next sibling to take is next sibling, so I think this goes child 1, child 2, and we're looking to find that ancestor. So, I think it's supposed to line up. But there's nothing coming out of here. Well, let's see. Let's see if we can get this to screw up. There's a teensy little data set here that is used, I guess, to sort of show off some things. Let's see if we can. I think to make this all work out, we need to go Actually, we could do it here. Make dir data's what's the name of the files? Our insert.tx. And we need to figure out the right format for these things too, I guess. Okay, just bare things. So let's, we're just gonna have this is better done over here. Actually, I don't know enough about Nano to do anything other than paste into it and save, really. Great, and we want to touch. Oof. Now, we can potentially run this thing, and instead of using oops. Oh, no, wait. What happens on line 180? It tries to... Oh. This is a... just a moment, sorry, this is not... So the, oh, I think I bet there is a new line that we don't really want, yeah. Great. So these have a different size, wonderful. There is a screw up. Let's see what that screw up is. So let's wander over here to where all of our heinous pile of printings have happened. And I'm really keen to see these two things that are being joined. Next sibling to take. And I think it's being joined with, which I guess is ancestor with next sibling. So, well, still I know. You can do a debug build because things are so small that we don't need the performance to actually get through the execution. So this should maintain the invariant as we climb back up, that everyone who goes in, the cardinality of this set isn't supposed to change iteration by iteration. We don't learn any effects, we just start from everyone who has a parent, everyone has a parent, but everyone who doesn't have a next sibling. Alright, what a mess, how could I have? So we have here a thing that we want to steal, and what looks like cancellation, actually. That looks grim. Let me put a consolidate in there just to so if that were the case, if this ends up with nothing, and in principle it's possible if we screwed this up where like our last join finds nothing. Yeah, okay, sorry, that's exactly right. So we want to not only, right, want to not only do these joins, but also make sure to keep around inner. I apologize for anyone who's like saw this an hour ago, but keep around inner as well. So we want to, when we do this maximization, we want to say like, you can either take a big step or keep whatever you've got, because you might already be pointing at the finishing point. So let's try this again. Ooh. That was already a reference, I guess. Expected reference. Found reference. What's different between these two things? Oh, okay. It's shaped slightly differently. Good. So inner child, and then the length. Okay, so we want to do, this is coming in as child, comma ancestor. So we'll do child length inc. All right, so that makes some sense, right? If we kept essentially this ancestor with next sibling would zero out, because let's imagine we had in some iteration pointers from everyone to the ancestor that they wanted. We do one more round of iteration, we do a join, and we find nothing, right? This is the thing that I've warned about, basically, that we would spill off of the top of the list because we failed to join with anything, and it's just an empty result. And the iteration concludes with nothing. Empty collection. Classic screw up. Okay. This is no different. Is this what we expect, or is this? I suppose I should put back in all of the other tests. Let's put this down at the bottom. Turn on all the other diagnostics, and we'll see if this catches on fire when we run it. We'll have to rebuild it before we run it on the big thing, because we don't actually want to look at all of these things. So it was super fun, right? Right. Yeah, I guess this is one of the differences between programming, in some sense, telling the computer exactly what to do, and sort of the declarative stuff you might do in Datalog, where you probably get the right answer a lot faster, and then you hit your head on performance for a while because you can't actually control what it's doing. We controlled it sufficiently well that we underived all of the facts. Well, looks like, in this example at least, we were fine. Or at least, we got through and didn't have any erroneous results. Let's see if the same thing is true. We run it here, but we're gonna try it essentially just on the big data now, and see big data, the 250,000 records. If it all works out, I'd be excited. We'll swap out the implementation for the new one that we've typed. We haven't actually fixed the blank stepping stuff yet, but in principle we could see if there's any dial movement on the elapsed time. Great. Siblings, I guess is a thing, whatever. No, it's still different. Oh, for fuck's sake. Why would you do this to me, data? Let's see if we can print out the things that are not actual data themselves. See how close we are. Oh, this thing is silly. We don't really want to see it. I mean, it's fine, but it's just telling us how long it took to compute some of these things. I was so confident that would be the reason. I mean, there's a classic debugging protocol where you it's wrong, and then you think for a while and you realize, haha, the one thing. And it seems like there's the second thing. Okay, so error, which is the gap between the two. The next element here, which, wait, hold on. This is like comically large now compared to this. Jeez. Hold on. Okay, well, this is definitely wrong. I mean, this is it's like twice, right? Let's go back and figure out what this silly thing is. So, we have first child here is enormous. That makes a lot of sense because that's the bulk. Like walking down these paths is the bulk of what's going on. Next sibling, pretty tiny, looks good. Substitutions, pretty massive. All right, we don't actually have this many substitutions, right? Or we're not supposed to, I don't think. On account of most folks don't have a sibling or aren't supposed to. So what's going on here? Next sibling isn't supposed to be that big. So how can we possibly, when we join these things, get something massive out of it? Has child is, I mean, there's some possibilities like has child. It's a distinct collection, right? So it's not increasing the multiplicity or anything like that. Next sibling to take, is that one of the things that we printed? God, I guess I can't read most of this. Next sibling to take, we looked at, and we were looking at its contents before. Semi-join has child, that's probably most of them, except there's probably a bug. Substitutions, much too large. So something is screwed up in here now because substitutions is enormous. Oops, sorry. Put these back in so that we can look at them. Oh, I shouldn't have cleared the buffer. Yeah, the intent, right, is that next sibling to take should not be large because next sibling isn't large. Next, this is just a few thousand. This is enormous. So this, unless there's a glitch with semi-join, should be at most the size of next sibling. And we're going to go and join it now with ancestor of next sibling, which this thing up here. We were hoping. Oh, I wonder. Oh. Okay, no, this is a good point. So we've in this iterative process we've found lots of links from folks going up, but we actually only this is one of these complicated things down in the original derivation. Like, well, I don't even remember why we have these. So when we do this join, we only actually want to do it for nodes that do not have children. All right, so when we climb back up from the left edge, we want to do it from the very last node. We don't want to do it from any of the intermediate nodes. So we want to do this ancestor with next sibling. I think we basically just want to do an anti-join. It's the easiest thing to type, at least. Anti-join with has child. And we'll just run that and see. So what we were doing, I believe, is producing a fairly massive set over here, actually. Pretty much everyone, well, not everyone, I suppose. Anyone in one of these long paths who doesn't have a next sibling, most of the nodes, they can go and figure out which ancestor they would use if they happen to be the someone without a child who needs to return up to an ancestor. But most of them aren't. Most of them have children. So although we need to involve them in this computation to do this repeated doubling stuff, they're an important part of the path back up, we really don't want to include them. Right? Their links are not relevant to us when we try to put things in a total order. Their contribution is to go down, not to hey, no panics. Well, it must mean it's correct, obviously. I'm glad we tested it. But yeah, okay. You're producing the same number of facts. For the moment, I'm going to diagnose this as, good enough for me at the moment. And we can comment out a massive amount of stuff here. And let's see how this behaves. We're going to want to steal this for a future. It's just going to tell us that's another different name, an ancestor. Next sibling. If we manage to sneak that in time, it will tell us about the number of iterations we do and how many facts are derived in each iteration. And the hope is that it's, well, probably more facts in total. So this was something that went up to 7,000 before. Hopefully more facts in total, though fewer rounds. All right, so that took 6 seconds, which sounds like it's more time, isn't it? Let's rerun it because I just put in that print line and saved the file. So we're gonna have to rebuild anyhow. So the 6 seconds, my thinking is this tells us that it's taking more time. it's we're doing more work, and that work is actually biting us, or potentially we've done a sloppy job of figuring out the right way to express this internally. Also very possible. But hopefully we'll be able to turn up some threads and Hold on, what's going on here? I wanted it to print out multiple iterations of things, and it seems like it's largely terminating in one iteration. Is that the right interpretation of this? Oh, crud. Okay. It's too smart for us. So in the first round, there are indeed exactly this many facts, and in each other round there are also exactly that many facts, so the change is 0. In each iteration, there's no change to the total number of facts, so it doesn't show us a diff at all. So this is a moment where we would need to do some trickery to get a report out here. I'm in the process of attempting to trick differential Dataflow. Use as collection. Yes. Oh, it's warning us about the T. That's fine. Yep, now we're just deleting the T. So all this is saying is take the stream of diffs that come in. There's 2 inners, that's unfortunate. But take the stream of diffs that come in, go into its timely data flow stream. This is just a stream of these update triples. And rewrite the update to be a nothing, because we're applying this map that throws away your data anyhow. And no one cares what your R was. We're going to change it into a 1. And this will make sure that things add up. Basically, we want to see a report for each round of iteration. And what we might end up seeing here is whatever that number was, 770,000 in the first iteration, and then everyone after that probably twice that. Good. So this is exciting. I mean, exciting for me at least. It does seem to take a logarithmic number of rounds. That's good. Logarithmic, I guess, in 7,000. That checks out. Yeah. The bad news, though, right, is that in each of these rounds, because these are largely long chains, in each of these rounds, we're basically fucking around with just all of the data, anyhow, because all of the data is involved in a long chain, and most of it is changing, right? So it's only the people. It's only once you've gotten yourself the right answer that you stop screwing around and stop changing. So, all things do stop changing towards the very end. For most of it, people are changing. And that's because these numbers, because it's most of the data and people are changing, it's just a whole bunch of work. So we definitely cranked up the total amount of work we had to do. I'm sort of curious to see what happens if we... So it's faster now. I mean, we added a lot of crap. If you're familiar with work that I've done, being excited about making things slower and then speeding them up more cores is not something to be proud of. Though we are in a state now where the total amount of time does increase, and I only have so many cores on my laptop here. It's legit to ask, did we actually do a good thing, or did we do... Okay, that seemed to make it... It's a little weird, actually. Oh, sorry, this is probably... So this part of the computation sped up still a little, infinitesimal amount, but a little bit. But we're probably eating the fact that we haven't fixed the other part of the computation yet. And so we're not getting through that any faster. But yeah, so I don't know. This is an interesting trade-off. Actually, let's scratch this printout, because that definitely costs. Right, that's something that we have to do that we're not the measurement itself takes a little bit of time. But it's an interesting trade-off where we've written a computation that does more work, and it actually does enough more work that it's pretty evident, right, that it's doing more stuff. The stuff is actually so much more that I'm a little surprised, but it seems to be that the single update per iteration we were doing previously was still better than doing updating everyone across 13 iterations, which still doing 8 threads. So 4, 2, 1. Right. So this I think this makes a lot of sense. I'm a little hesitant to recommend it though, but I think this makes sense in that we've tweaked the algorithm to one that scales better now, right? In the sense that each of these 13 rounds, if we have more cores, and I have I think like 16 on my desktop, I could go and grab that. But if you have more cores, the work now scales a bit better. Potentially incrementally updates a bit better also because the dependency chains are not nearly as long. But because it's just more total work, you shouldn't feel great about yourself until you actually get faster than that single threaded number. Which, it sort of looks like 8 was headed towards here. This was, no, 4. Sorry, 4 was headed towards, we had previously, I think, 2.3 or something like that. So this is on its way towards that. And you could imagine, you'd have to imagine, for the moment, that fixing the value blank star stuff would also cause 4 cores to speed up a little bit. We're going to add more work, but then potentially speed up. And it's possible that it would actually move it in the right direction with respect to the single-threaded baseline that it just iterates really fast. So I'm curious if the right thing to do is dive into that and code it up. It's pretty similar. Now that we've seen this once, hopefully we avoid making the exact same mistakes a second time. Another option is to try to figure this thing out here and see if there's... I think the reduce is a bit grotty. Like, you'd love to not have the reduce, because the reduce is always... as far as I can tell, there's always either 1 or 2 elements heading into the reduce, right? Either you just did a big power of 2 leap, or you're staying put because you missed. Right, so like you could potentially rewrite this as do this join, and for everyone in inner that didn't get something out of the join, just put in their value from inner, which saves you this reduce. Basically, this reduce is a sort of stateful operator that needs to do a fair bit of work, and we're doing it feels like such primitive work that you could possibly express the core of this as a data parallel operator itself, or sorry, like a few concats and joins and stuff like that, which is... So we could look into optimizing the computation a little bit here to see if we can just draw down the constants across the board. I wonder, maybe I'll do that on my own time, and we might look into the value blank star thing next. Though actually, what I think I'm going to do now is pause. It's a good time, I think, to take a break. I can stretch and do some stuff there. We don't need to solve all this at once. And also, I think we've reached a good thinking point, basically, that things are slower now on a single thread without some additional work. And that's a great, teachable moment, I guess, that concurrency, at least in the example we've seen here, concurrency parallel scaling can come at some cost, and yeah, too bad. Then there's a thing to think through about what you like to have. Would you like to have a really fast single thread implementation, which makes a lot of sense in some cases, or a scalable data parallel implementation? But I think we'll stop for the moment. Appreciate all of your eyeballs and your time, and we'll be back with the value blank star stuff. And if I happen to notice any silly performance things in the meantime that save factors of 2 or 3, that would obviously change the calculus substantially. But thank you.